Our last talk is going to be a virtual one. And the speaker, Xiaopeng, will be online for a live Q&A session. Okay. This is the Lunar paper, right? Okay. So, Xiaopeng is a PhD student of the Data Center and Engineering at East China Normal University. His research interests include storage system, operating systems, and distributed database systems. And here is his talk.
Hello everyone, here is Xiaopeng Fan from East China Normal University. Today I am going to share with you our recent work, Lunar, and show you how we build a native table engine for embedded devices. I will introduce the research background, motivation, design points, performance evaluation, and the conclusion in turn. I/O performance has been recognized as one of the key factors affecting the system performance of embedded devices. Traditional embedded devices I/O system consist of a set of host software and storage devices. Embedded devices employ flash memory for persistent data storage. The high write stress negatively not only reduces performance, but also impacts on the flash storage lifetime. Then, low-end and mid-range embedded devices with relatively low prices and limited resources are prevalent in the market. Traditional host software has a complex multi-layer storage stacks, which includes database, file system, block layer, FTL, and driver layer. Recently, research efforts have been made toward various levels of the I/O stack to improve the performance, and they often focus on optimizing the individual layer within the software stack. Now we perform a performance study to understand how database utilize the underlying storage. Here we use mobile bench with SQLite as its test database to perform 4 kilobytes insert operations. We collect the bandwidth and the block layer and the SQLite layer during the insert operation. The figure shows that SQLite suffers from significant bandwidth loss compared to the block layer for all three file systems. Drilling down, we collect the bandwidth of the file system layer on the I/O path. As shown in the figure below, we find that compared with the block layer, the file system layer loses 11% to 48% of bandwidth, and the database layer further loses 62% to 79% of bandwidth compared to the file system layer. Indeed, a file is an abstraction of a collection of blocks, while the table is an abstraction on top of the file. Each layer of abstraction requires additional data structures. This observation gives us an insight. Multi-layers of abstraction exacerbate I/O amplification, which not only reduces the bandwidth utilization, but also shortens the flash lifetime. To address this issue, our key idea is to remove the file abstraction and perform cross-layer design across the database and the file system. Constructing table structures directly on storage devices presents a novel solution, but it also poses some unique challenges. How to perform cross-layer optimization while considering compatibility. How to design table storage management, including storage layout and allocator. How to build the system to adapt to resource-constrained embedded devices. We propose Lunar, a native table storage engine for embedded devices. It has the following 4 design goals. Lightweight. Lunar performs cross-layer design that removes the file abstraction and directly stores tables on the device, while providing SQL-compatible APIs. storage efficient, Lunar employs a type-aware storage layout that considers the access patterns of different data types. Additionally, it uses a variable size block allocator. Modular. The modular architecture of Lunar allows for building a table storage engine by selecting specific models to adapt to resource-constrained embedded devices. Flexible. Lunar offers 4 flexible consistency modes to balance resource consumption and consistency levels for different embedded applications. This figure shows the traditional and Lunar's I/O system. Lunar performs cross-layer design by integrating the database and the file system layers. It removes the file abstraction and directly stores tables on the device. Considering compatibility, Lunar provides SQL-compatible APIs such as create table, insert, select, and update. Lunar gains direct control over the storage management, allowing the design of an efficient data layout and allocator that corresponds to database access patterns. This figure shows the high-level layout of Lunar data structures within the storage device. While Lunar may share some similarities with file systems, it is crucial to recognize the fundamental distinction that it removes the file abstraction and instead stores tables directly on the device. Specifically, Lunar divides the storage space into file zones. The super stores global system information, such as the total space size, number of tables. The root zone includes the root table and its metadata. The meta zone serves as a metadata collection for common tables. The data zone stores the data of common tables. And the log is used to guarantee data durability and transactional rights. As shown in the figure below, the file zones are divided into 3 regions. Different data types exhibit distinct access features, including access granularity and sequential or random access. We categorize them into different regions according to data types. Region 1 comprises a set of data blocks with the smallest storage unit, and the 3 zones, super, root zone, and meta zone, belong to this region. This region stores metadata information that is small in size and is often accessed randomly. Besides, region 3 consists of large blocks that store the log. Given that log involves large and sequential I/O operations, it is advantageous to have a spread large and contiguous region to accelerate the logging process. Then the data zone belongs to region 2. Unlike traditional allocators with fixed size blocks, which result in fragmented files, region 2 uses a variable size block allocator to reduce fragmentation. Each class includes data blocks with a specified size. Size class 0 contains the smallest blocks. Subsequent size classes contain blocks of exponentially growing size. Note that the minimal and the maximal size classes, as well as the growth factor, can be configured based on the workload. In particular, setting the growth factor to 1 results in a traditional fixed size allocator. Embedded devices have limited resources. Lunar adapts a modular design. These models are classified into 3 categories. The basic model is required, while the following 2 are optional. The basic model is the core of the table storage engine, providing fundamental storage capabilities. System optimization models provide services that apply to all tables in the system, and each table can customize its table optimization models. Furthermore, Lunar makes a trade-off between resource consumption and consistency. In general, weaker consistency results in lower resource consumption and better performance. Lunar provides for consistency modes that range from weak to strong. Due to the time limits, these design details are omitted in this talk. If you are interested, please check out our paper. Next, we show some experimental results of our work. The experiments are tested on a K210 core board with a 2-core 64-bit RISC-V processor, 6 MB of RAM, and a 32 GB SD card. We compare Lunar with the SQLite, the most widely deployed database engine in existence, as well as with the latest database for embedded devices, FlashDB. We run Mobile Bench, YSB, and the SQLite Bench. We first report the results of the latency. We run the YSB benchmark with different read-write ratios and skewness. From the figure, we can see that under read-only workloads of different skewness, Lunar's average latency is 49% and 57% of SQLite and FlashDB respectively. This improvement is due to the cross-layer design, which reduces software redundancy. By removing the file abstraction, Lunar provides a shorter and more efficient I/O path to accelerate the data processing. Besides the reduction in response latency, we are also concerned about the improvement in throughput. We use Mobile Bench to analyze how databases utilize underlying storage performance. We perform SQL requests and collect the database layer and the block layer bandwidth. While performing insert operations using SQLite's rollback mode, there is an 81.7% bandwidth loss compared to the block layer. When SQLite operates in write-headlong mode, there is a performance improvement compared to the rollback mode. However, there is still a 70.5% bandwidth loss compared to the block layer. In contrast, Lunar constructs the table abstraction directly on the device rather than relying on the file system, and Lunar achieves a higher bandwidth utilization of up to 81%. This table shows the ROM and RAM usage of systems. Lunar reduces ROM and RAM consumption by 80% and 93% compared to SQLite. It is due to the fact that Lunar has a lightweight software stack, leading to reduced resource consumption. Furthermore, its modular architecture allows the basic model of Lunar to offer table-based storage service and adapt to highly resource-constrained embedded devices. In conclusion, Lunar is motivated by the fact that multi-layers of abstraction exacerbate I/O amplification, which not only reduces the bandwidth utilization but also shortens the flash lifetime. We propose Lunar, a native table storage engine that removes the file abstraction and provides SQL-compatible APIs. For storage management, Lunar employs a type-aware storage layout that considers the access patterns of different data types to optimize performance. It designs a variable size block allocator to reduce fragmentation. Further, given that resources on embedded devices are limited, Lunar adopts a modular architecture that enables module selection on demand. It also offers 4 optional consistency modes to balance resource consumption with consistency requirements. Experimental results show that Lunar performs better performance and less resource consumption. That's all. Thank you for listening. I'm ready to answer questions.
All right. Hello, Xiaopeng, can you hear us? Hello, can you hear us? All right.
Hello.
All right, great.
Can you hear me?
Yes, we can hear you. Is there a question from audience?
So your design remove the file abstracts and storage the table in the device storage device. So can you introduce the impacts of this design and how do you ensure the compatibility?
Okay, thank you for your question. First, for the compatibility, Lunar provides interface similar to those in traditional databases, such as create table, insert, and select. Further, Lunar is primarily designed for managing the structured data, which can indeed introduce challenges in terms of compatibility for the file system-based software systems.
Is there other question from audience? Then let me ask one last one. So related to that one, where you are removing the abstraction layers, can you talk about the downside of doing it, like software maintenance or and so on?
Okay, so the lines are designed partly to reduce engineering and complexity. However, multiple lines of abstraction lead to severe bandwidth loss in the I/O path. Indeed, the removal of the file abstraction in Lunar has posed certain challenges to the maintainability of the system. So this compromise was made in our pursuit of high performance. Thank you.
All right, thank you. All right, then this concludes our session, and then I will hand over our mic to our general chair.
Well, yeah, so thanks to all of you who stuck with us to the very end. Thanks for attending. Thank you for the presenters, for the great talks. Thank you also for Donghyun for selecting good papers. And I think you were a PC member, right? No? Okay, we don't. Do we have a PC member? No. So all the PC members did also great work. And I hope you consider LCTS again in the future, next year. And we hope to see you all then. Thanks very much.